Welcome to the Explainer. We're skipping the fluff today and getting right into exactly how Cambridge examiners award top marks for crystal structure questions in Physics 9702. We're going to deconstruct the exact strategy you need to conquer primitive and non-primitive cells. This is all about moving completely away from just memorizing definitions and actually understanding the internal physics that examiners are literally desperate to see. If you've ever walked out of an exam feeling great, only to get your paper back and realize you dropped massive grade boundaries on a supposedly simple explanation question, you are in exactly the right place. We're going to dismantle the ultimate trap that almost everyone falls into and build the precise architecture of a top-band answer. Picture this. You're in the exam, the clock is ticking, you read a question about primitive cells, and you write down a sentence exactly like this quote. A primitive cell is a basic crystal cell, and it is used in semiconductor wafers. It feels pretty good, right? You mentioned the term, and you even threw in a high-tech real-world application. You move on to the next question, totally confident you just secured those points. But here's the harsh reality. That scattered collection of facts might feel entirely correct to write, but it earns exactly 0 marks. Nothing. Ouch. Why does Cambridge penalize this so heavily? Because it simply states a term without explaining what physically happens. It gives a real-world application, but completely fails to link it back to the underlying microscopic reason. The examiner doesn't care that you can memorize a buzzword. They need to see that you understand the internal physics. So let's eliminate this massive grade boundary risk right now. Let's look at the 4-step framework for escaping the 0-mark trap. In a moment, I'm going to share the exact clue examiners use that changes the game completely. But honestly, it won't make a lick of sense unless you have the right architecture in your mind first. If you don't know the structure of a perfect answer, even the most glaring hints in the exam paper won't save you. You need a disciplined, high-retention framework built on cause and effect. And this brilliantly illustrates our core concept. If you can explain these 4 specific stages in order, you're going to have the depth needed for short and extended questions alike. Step 1, define the idea. Just state what the structure actually is. Step 2, and this is the crucial bridge everyone misses, describe the microscopic mechanism. What are the atoms actually doing? Step 3, identify the measurable consequence. Because of what those atoms are doing, how does the material behave on a macro level? And finally, step 4, connect that consequence to a specific material or device application. This logical sequence builds a true, unshakable understanding from the ground up. Moving on to decoding crystal cells from atoms to applications. Instead of just defining these cells as simple geometric shapes, we have to explicitly state their microscopic mechanism. When you sit down for that paper, your mind must immediately jump to 3 things: packing, bonding direction, and defect tolerance. The fundamental physics here is that these specific crystal arrangements, whether they're primitive or non-primitive, directly control internal packing, bonding direction, and defect tolerance at the atomic level. This is the physical cause in our cause and effect chain. It's the engine driving what's physically happening inside the material. So the crucial takeaway is that you cannot simply state a real-world application without linking it backward to this internal microscopic reason. Think of it like a vintage watch. You can't understand how it tells time just by staring at the dial. You have to understand the microscopic arrangement of the gears inside. The entire macroscopic behavior of a solid, whether it conducts electricity, its structural strength, or how it responds to thermal stress, can be interpreted entirely from what happens internally at that atomic or carrier level. This is the golden rule for these questions. Now let's look at the examiner's correction and spot the error. Notice how an elite answer builds a continuous, unbroken chain of physical reasoning. A flawed answer just names a device. It's just a scattered keyword solid. But a top-band answer is a highly disciplined paragraph. It starts by stating how a specific crystal arrangement dictates internal atomic packing. That packing then dictates the solid's observable behavior, which finally makes it perfectly suitable for a specific device. It seamlessly connects the atomic cause directly to the macroscopic effect. We also need to map out exactly how to respond to Cambridge command words, because your approach is to shift depending on the prompt. If they say define, state the term purely in its physics context. Simple. But if they say explain, this is where you absolutely must give the microscopic basis plus the macroscopic consequence. If they ask you to compare, don't just list facts. Draw clear boundaries between related concepts so the examiner knows you haven't jumbled ideas together. And if they ask you to give an application, you don't just state a real-world use. You have to provide a physical justification, linking that use all the way back to the crystal structure. Let's jump into real-world material impact and why this matters in technology. This is where we apply the final step of our framework. Real materials in electronics and aerospace behave differently, specifically because their internal structures dictate their performance. Take semiconductor wafers, for example. Their non-primitive diamond lattice structure dictates the precise carrier pathways needed for modern computing. Or look at aerospace turbine blades. They require specific crystal packing to provide extreme defect tolerance under immense thermal stress. What about structural alloys? Their specific internal atomic packing literally alters their macroscopic tensile strength. And even gemstones get their brilliant optical properties from their strict internal bonding directions. Understanding this cause and effect chain is what makes the physics stick in your brain. Time for a memory trigger checkpoint to lock this all in for revision. If you ever find yourself freezing up during an exam, and hey, it happens to the best of us, ask yourself this one foundational question to immediately trigger your memory. What changes inside the solid? Seriously, don't think about the outside yet. Don't think about the application. Ground yourself in the physics. Just think about the packing, the bonding direction, and the defect tolerance. If you can answer these 4 prompts aloud from memory right now, your understanding is completely locked in. 1. What is it? 2. What changes inside the solid? 3. What can we observe outside the solid as a measurable consequence? And 4. Where does this matter in technology? This logical progression is your ultimate revision tool for hitting every single requirement on the examiner's rubric. So, you've mastered the crystal structure framework that perfectly solves the 0-mark trap for standard explanation questions. But honestly, it still leaves you exposed to a massive grade boundary risk when you encounter high-level data evaluation questions. You can explain the physics of an ideal crystal perfectly now, but what if Cambridge gives you a table of conflicting experimental variables? What if the data presents anomalous results regarding a material's defect tolerance and then asks you to evaluate the contradictions? Knowing the ideal framework just won't be enough if you don't know how to navigate the messy realities of experimental data. To truly master this physics, you don't just explain the ideal, you have to be able to evaluate the contradictions. How exactly are you going to navigate a table of conflicting variables on exam day without dropping critical marks? Well, to discover the mandatory correct pathway for top band valuation, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE. We are going to unlock that exact evaluation framework in our next explainer. You won't want to miss it.